This looks to be working. And great. All right. Hello, welcome to this video. And within this video, I'll be explaining linear and nonlinear regression in terms of the Anton equation. And I'll also be using Google Colaboratory, which is in a different form of Python, to code out this relationship and give you examples of how nonlinear and linear relationships work according to data. In this case, we'll be using data downloaded from GitHub. Well, I'll get to that in a second. So first of all, we can ask ourselves, what is the Anton equation? Well, let's go to Google real quick. The Anton equation is we can see right here, class of semi-empirical correlations describing the relationship between vapor pressure and temperature in pure substances. Now, you can take the definition and take of it as you will. Well, really, we're going to be looking at the relationship between vapor pressure and temperature. So we can look here at this, we'll be using this example of the equation here. And we'll be looking at, here we can look at some key parts of this equation. First here, the log base 10, as you can see here, P, that stands for our vapor pressure. And we have T here representing our temperature in Kelvin, and our vapor pressure is also in pascals. And we have these three variables here, which we can use to manipulate the equation. And we'll get into that in a little bit, talking about in the sense of linear, nonlinear. So first of all, we can actually use this equation to manipulate some data, which I will be grabbing from our GitHub site, which we have on our Canvas site here, our professor posted. So we can go to GitHub. And let's see. GitHub is a site in which we have a bunch of code that is readily available for us to download and use in Python. And we are going to want to use this data packet right here. And what you see right here is two columns of numbers. In this case, the left column represents temperature data, which is in Kelvin. And on the right side, we have vapor pressure, which is in pascals. Now, as of right now, we could go about by just copying and pasting this site and just coding it into Python. But this would be a little harder in the sense that this GitHub website has a bunch of other different kinds of scripts in it, has different kinds of software that would make it kind of difficult for us to code in. So rather than coding in the entire site, the page, we are going to go and click this raw button. And this transfers that data before, these are the same exact numbers as before, into just a text file. It makes it a lot easier for us to transfer the data over to Python and work with and manipulate. And so we have the same temperature in Kelvin, vapor pressure in pascals. And you notice here we have a comma in the middle that is separating these two columns so that Python recognizes there is a separation and these are two separate values and not one giant glob of text and numbers. So we are going to copy and paste this website address. And now we are going to go over to Google Colaboratory, which I already have a script ready and open. So Google Colaboratory is a version of Python that is free, easy to download, takes no unnecessary outside downloads, updates, or anything. It is ready for us to use. And it is a free Jupyter notebook that we can use at any time. And it's also running by Python. So now we are going to first code in our text that we just got from GitHub. And we are going to first use the command wget, and this calls in that text file which we had. So we're going to put the website address here and use Shift Enter, and that actually just called that data in from the GitHub site. So now we can look back here, and yep, it is right here on the side tab. We have a water vapor pressure CSV. So that is the file which we just downloaded, the text file. So now, in order to start working with this text and start manipulating it, we want to import some different code here. So import numpy as np, Shift Enter, and now we can start using the data and start working with it. So we're going to say data, which we just downloaded, equals np.load text, and we put in quotation marks the name of the file which we want to download and work with. So water vapor pressure, I need to spell it correctly, .csv. Put a comma, and now we have to identify the comma that is separating the text file, as I said earlier, so that Python doesn't see it all as one giant blob of text. So in this case, the Python calls this comma a delimiter. So we have to specify the delimiter, in this case, which is a comma, that is separating the two data columns in the text file. So we are going to put delimiter equals, and then in quotation marks, a comma. And that should be it. So Shift Enter. All right, so now we have our data called in here. So now if we just type in data, Shift Enter, it calls in that same array which we had originally from the text file. Temperature in Kelvin on the left side, and vapor pressure in pascals on the right. All right, so now that we have the data called in, now we can start actually thinking about graphing it. So first of all, we want to assign variables to these two columns. So let's say we're going to call x is equal to, well, actually, no. Let's start with t, temperature, is equal to data. And we'll put it in brackets. And an important note, in Python, when working with lists and arrays, the identifier, in which we start off counting like column 1, column 2, column 3, or row 1, row 2, row 3, so on and so forth, it starts with an identifier of 0 instead of 1. So the first value, the first identifier, is 0 in this case. So the data for temperature, we are going to call in everything from the top to the bottom is an identifier of 0, column 0. So now we go down here, and now we call in the second values of vapor pressure, and we are going to call those, in this case, log P. Log P. And we want to call this in, since we're using a log, we have to use a specific function. So log 10. And we can put data, and the same thing before, put data, put the brackets, and colon, representing everything the list will be called from the first value to the end, comma, and 1. In this case, 1 is the second identifier, which means it is the second column in this array. Go outside here, Shift Enter. So now that we have this, we can now start going about and thinking about graphing this. So we are going to import some more software to use with. So we are going to start to import from Plotly. And Plotly is a software that allows us to make subplots, different graphs, and stuff like that. So plotly.subplots. Import make underscore subplots. All right. Now we got another second here, and now we can start to import plotly.io as PIO, and now PIO.templates default equals, now this command right here, this last command, actually makes the background of the backdrop of the scatter plot, which we're going to make, darker. So it allows us to see the data points easier and make it a clear picture for us to work with. Dark. All right, Shift Enter. Oh, we have a problem here with the syntax. Plotly. Yeah. Sweet, that works. And now we can start actually making our graph here. So the graph of the data, we are going to use fig equals make underscore subplots. And we're going to do rows equals 1, columns equals 1. We have one row, and one column. Sorry. We're going to do fig dot add underscore scatter. In this case, this means scatter plot. And we are going to say our x value, our independent variable, on the x-axis is going to be equal to our temperature values. And our y values, our dependent variable, would be our vapor pressures, so log p. And we are going to use our markers in this case, or our data points are going to be in the form of markers. So we're going to do mode equals markers. And the name of our plot, we'll just name it raw data. All right, sweet. And then the last thing, we're going to update this last line of code here is going to make our graph, all the data in a, we're going to shift the borders of our graph so that it is easier for us to work with and see the data points, so that everything is not stretched out and hard to read on the scatter plot. So just go to layout, and we'll do a width of 800 and a height of 600. And shift enter, and this should give us a plot. All right, sweet. So now we are able to see the data points from the graph before previously, or not the graph, the array before that we got from our text file up here. We're able to see it plotted out, and we can actually begin to interpret the graph and see if it makes sense. So, quick check. The boiling point of water in Kelvin for our temperature is 375 degrees, roughly right there. So we can look up here around 375 degrees. This puts us at about 10 to the 5th pascals, which is about 100,000 pascals, which makes sense. So our graph of data here, our scatter plot, makes sense. All right, so now we're going to shift gears and actually look over here and pull my paint real quick. And now we can start looking at this in a sense of nonlinear regression. So let's say we know we have a plot now. And we have data points. And now we have a model that is going through those data points. And we have our equation. So we have log of p equals a minus b over t plus c. Okay, so with these data points that we have, we are going to try, we want to minimize the deviations from our model. In this case, we want to take these distances from our model and our data points and make them as small as possible. We want to make sure our model runs as closely to these data points as possible. So in order for us to do this, we're going to use a method of just adding up the deviations and do a summation. So let's see. Get another marker here. So we're going to do a summation. So the summation of log p, in this case log p represents, or log pi in this case, represents the start of our data, where I is equal to 1, and n represents the end of our data. So log p right here represents our data points, and we are going to take the difference from this from our model. We want to make the distances or the error as small as possible. So one second, go back and take this out. And let's do a minus b over t plus c. Okay, so now we have our summation. So you notice here, there's a problem with what we have right now. So we have our data points, and we have some data points that are negative in the sense that they're below our model. And we have some points that are positive. So in order for us to be able to work with all the data points in a similar fashion, we need to make sure they all have the same sign, meaning that they're all positive. So in order for us to have this near reality, we need to take the absolute value or square our entire equation, which will help us have all of our data points be an even sign or a positive sign, an even sign. So now we square it, and this right here is known as our sum squared error. And we're trying to minimize the deviations from these points away from our model. So we're trying to make this distance as small as possible. So we can do this by manipulating the variables a, b, and c. So now we can look at this in a coding sense. All right, so we're going to need to make a function to represent our sum squared error. So we need to define it first. So define sum squared error equals sum vectors. In this case, we want to unpack that and say that our vectors are equal to a, b, and c, which will help us minimize those deviations in our model and data. So a, b, and c equal our v here. So now we can start looking at return. So we're going to return our sum squared error. So we do np.sum. And we want to, let's see, sum squared error of, let's do x equals t again. And actually no, let's go back. It's going to be sum squared error of log of p. So log p minus a, parentheses, a minus b divided by, in parentheses, t plus c. All right, so now that we have these, you're going to want to square the entire thing. So square it. All right, sweet. Shift enter. So now that you have that called in, we're going to want to minimize the deviations from in our model in our data. So in order to do that, we are going to want to look up the syntax for this. So SciPy optimize minimize. So we look this up. Actually, we are able to look up a page that actually gives us the syntax on how to actually run the SciPy optimize minimize function here. So we can actually just copy it down from this page. So, all right, just do this. Sweet. All right, so we are going to want to import, or just say, to import the minimize. So we're going to go down here and do from SciPy optimize import minimize. All right, and shift enter. All right, so now we have that. We can actually start working with our data here. So we're going to want to minimize our sum squared error. So minimize our sum squared error. And we are going to take some initial guesses about the parameters of our sum squared error. So let's put this in quotation marks. Let's give our first guess 10. Let's do 1 and 0 is our first guesses. Now the thing to keep an eye on when the minimize function in general, your guesses are very important to whether the graph will look right or not. A bad guess will give you a graph that does not look good. It will not have a line that'll run close to the data or anything like that. So guesses are important in this case. You want to make sure your guesses are somewhat usable and not just any random numbers. So you want to test them. All right, so let's actually run this and see if this works. All right, sweet. So it gives us some values in an x. And let's see if we're able to work with these. So let's say a result equals minimize. Let's see if this works. All right, so if we do res.x, yep, it calls us the same values as before. So now we can actually just put on since we're only looking for the x values here, let's just put on x to the end here. And we can actually assign some vectors to this, or some variables. So let's do some new variables, a, b, and c, but in this case, we're going to name them a little bit differently. So a, b, nonlinear, a underscore nonlinear, b underscore nonlinear, and c underscore nonlinear. And okay. So now that we have this, we can actually think about starting to graph this and look at the relationship in a nonlinear sense, regression sense. So okay, we can do fig dot add underscore scatter, and we are going to still use the same x variable for temperature. So for independent, we are going to use t. And for our y, things are going to change a little bit here. So we are going to want to put in our new values, a nonlinear, b nonlinear, c nonlinear, into our Anton equation. So we are going to do, let's see, log p or no, wait. It would be, let's see, it'd be y equals, yeah, a underscore nonlinear minus b underscore nonlinear divided by, in parentheses, t plus c underscore nonlinear. All right, sweet. So now that we have this, we can go outside of that, parentheses, put a comma here, and in this case, we're going to want to use lines to represent our model running next to the data points and see how closely we can get it. So let's do mode. In this case, we'll do lines instead of markers as before. So we're going to do mode lines equals sign here. And we will name this, let's do ant, so for Anton equation, nonlinear. All right, sweet, that should work. Let's run that and do this. Oh, we have a problem with our data here. We seem to have some sort of issue with our data. So, like I said before, our guesses are for our minimize function, are very important here. So in this case, we got values that were our guess for a model here gave us way off from the data points. So we're going to want to look up here and see if we made any mistakes. So let's see. Turn np.sum. And let's see, log p minus ab divided by t plus c. Okay, so I think I found my issue here. So I did not have a period on this side of the 0. So I think I kind of messed up the syntax with everything here. Also, I think, like I said before, the minimize function, it is very important with your guesses based on how your graph will turn out and everything. So I change my 10, marginal guess of 10 here in this slot, and change it to about a 1, just to see if it does anything. So everything's saved here. Let's run this again. And actually, let's restart all. So we don't have very many of these here. Let's see how that looks. All right, sweet. So as you can see here, it looks a lot better than that bold red line up top here in the data down below. So we now have a model that runs a lot closer with our guess now. In the fixed syntax, we have a model that runs a lot closer to our data. So now we've just demonstrated the nonlinear of regression in terms of the internal equation with random guesses. So now what if we wanted to take the guessing element out of it and wanted to look at it more of like just getting answers, having numbers given to us rather than guessing for those numbers? So we can look at this in the sense of linear regression. So let's go to the paintpad again. So we're going to start off by writing down Antone's equation again. So we have log of p equals a minus b over t plus c. And what we're going to do here is we're going to manipulate this equation and move around some variables in order to get this into a term of matrices, and I'll show you that in a second. So let's see, we're going to start off by getting the t plus c off of the bottom of the denominator on the right side, and we're going to do this by multiplying it against a on the right side here, and also log of p. So this is going to go to t plus c times log of p equals, and now we're going to distribute the, let's see, the a to the t plus c on this side. So we're going to have a t minus, no, it's addition, right? Yeah. So a c minus b. All right. So now that we have this, we can start moving this around a little, simplifying it a little more. So we're going to distribute the t and the c, and we want to make sure that we have t log of p only on the left side. And we're going to move the the c log of p to the right side. So our equation is going to simplify even more and look like this. So we can start working on this in matrices. Okay, so we're going to have, it's going to look like t log of p equals a t minus c log of p plus ac minus b. All right, so now that we've moved around this equation and simplified it down, now we can start thinking this in terms of matrices. So now that you notice here, our matrices, now the a, c, and b are still variables or vectors that are undetermined. We have no clue what they are. We are trying to look for these numbers, and we're going to use coding to determine them. So we have the terms of temperature, which is our first matrix. We're going to create a design matrix. That was terrible. Try that again. So we have temperature. Right here, I'm going to use a different color. We have our temperature, the first column. We have a negative log of P. And we have a column of ones. That's what a design matrix is. A column of ones, and then our two variables. So temperature, negative log of P, and ones. So we're going to have multiple values of these, or iterations. So 2, all the way down to the final value in our list, T of n. And we're going to do the same thing for the negative log of the vapor pressure. And we're going to have ones down all the way. All right. And so all the way down to the bottom of the very last one. Sorry, this is terrible. I'm drawing with a mouse. It's quite hard. So, and then we have n. All right, so this is our design matrix. It is actually in the form of a, it's not square. So it is just a matrix of data. And this is in the form of 3 by n. This is a 3 by n matrix. And we're going to multiply this against our unknown vectors, undetermined vectors, a, and we're going to look at this real quick. These are going to be our unknown vectors. We're going to actually simplify this and just give it a simpler form, a variable of, let's just say, d. So this is actually just d. All right. So let's say, we're going to give this, so it's going to be A, C, and D. These are our unknown vectors. And we're going to multiply these, and they are going to equal our final matrix of this right here. This is our transformed data that we're working with, our temperature and our log of P. So this is going to be temperature 1 times, well, it's going to be a different column, but log of P. And it's going to go down like the ones before in the previous column, the design matrix over here. We're going to have different iterations of them, all the way down from the first value all the way down to their final value. So now that we have these, we can actually simplify these down into variables of their own. We can turn this into a, let's just say, give this a variable x. So all this is here is an x. Let's give this the variable of v. And let's just say this is y. It'd be easier to work with here. So now we want to make sure and turn this, right now this design matrix is kind of hard to work with because it's not square. So we want to make this, the data square in here. So the way we're going to do this is we are going to take the transpose of this design matrix. So let's see. We are going to take the transpose. So let's actually, let's get a new. We'll save this. We'll just give this a name of notebook. Notebook. We'll save that. Actually, it doesn't really matter if we do anything with it. Okay, let's just get a new one. All right, so we have these parameters here. So now we want to take the transpose of that design matrix. And let's do, so taking a transpose, actually a transpose is flipping the matrix on its side or a different direction, and it makes it square. So we're going to multiply x, which we had previously, x times v, equals y. We are going to multiply x by its transpose and flip a design matrix. So what we do here, we have to do on the other side. So now we need to do x transpose multiplied on this side by y. So now we have that. So now what we're going to do is we're going to take the inverse of the x transpose multiplied by its x. And we need to do the same thing on both sides as well. So now what we're going to do is we are going to do x transpose multiplied by x. Take the inverse of that and multiply it against x transpose of x multiplied against v equals, I need to do the same thing to both sides. So we take the inverse and multiply it by this over here. We need the same thing over here. So we do x transpose times x minus 1 multiplied against, bring this down here, x transpose times y. So now this right here is very important. This turns the design matrix that we had before with our temperature and our negative log of the vapor pressure and our column of ones, that turns that into a identity matrix. Now, an identity matrix is a matrix that has a diagonal of ones down its center. So this is now an identity matrix. We're going to turn that into I. And now we can look at this. This right here is the equation we'll be using, or relationship we'll be using to actually find out our guesses for the A, C, and D and B here for our model versus the data. And we'll be using that to minimize the deviations. So this is very important here. So we can go back to our code now and start actually coding this in. So now what we're going to do, we are going to do x equals, let's see, np dot c underscore. That's going to give us columns. And the first bit of the column is going to be, let's see, it's going to be temperature, followed by negative log of the vapor pressure, followed by, let's see, it's going to be, it's going to be np dot ones underscore like. Now the column of ones is going to be in the same form as the column of temperature values. So you're just going to say like T. Okay. And should be good. Shift enter. Oh, we have a error here. Might need to be brackets. Yeah, might need to be brackets. Sweet. All right, now we have that. So now we identified our design matrix. So now we can work from here. So let's see. We want to take the transpose of our design matrix and actually make it square. So I'll show you that now. So we're going to do x dot t, and shift enter. And that actually gives us our transpose here. So now if we want to multiply that by t, and now in Python, multiplying matrices, you have to use the at symbol. So multiplied by x gives us a square matrix. All right, sweet. All right, so from here, we can actually start to continue with what we were doing before. So the rest of it, it was taking the inverse of this. So to take the inverse, we need to do NP dot linear algebra. Yeah, linear algebra dot inverse. And now that we've done that, we do this, put the parenthesis on that, multiplied by, now the other side of the equation we had before, I can pull that up again. We were wanting to multiply the inverse of x transpose times x multiplied by x transpose multiplied by y. Now y before was the column of, let's see, it was temperature multiplied by the log of P. All right. So let's see. We're going to do x transpose x dot t. I'm going to make sure also that it's very case sensitive, Python. So we want to make sure that we have all of our variables, x is capitalized, t is capitalized, everything is the same. Otherwise, it will cause a syntax error. So we have that multiplied by, now in this case, the y wasn't a matrix, it was inside of the matrices, so we want to multiply those together. So we'll treat the outside of it like a matrix, but the inside, the multiplication is actually just t times log of p. Okay? And enter. All right, sweet. So now we actually are getting to some guesses here. Like I said before, previously we were guessing 1, 1, and 0. And we got lucky in this case with our nonlinear model. So now we are starting to get some actual guesses we can use here without actually just throwing in random numbers. So let's see, we want to actually give these data values names. So let's go ahead and set this equal to, let's say, a underscore linear equals the first value here. The second value will be equal to b, no, it'll be c underscore linear. And the final value will be equal to d underscore linear. All right, sweet. Hit enter. All right, now that we've done this, we want to actually take out the d and find b again. So we can, because before there was no d variable, we substituted the b out originally and put in d in our equations before, dealing with Antone's equation in the linear sense. So we want to bring back in b. So how do we do this? B is actually equal to a times c minus d. So let's go ahead and do that again. So b underscore linear equals a underscore linear times c underscore linear minus d underscore linear. All right, sweet. So now that we know this, let's go ahead and just find out what a, c, or a, b, and c are now. So a underscore linear, b underscore linear, and c underscore linear are equal to these variables right here. So these will actually be our guesses here. We're going to throw up here and try and test and see if the values we got from the linear method are any better than our values that we just guessed with in our nonlinear method for our model. So let's go up here. So it was 10. 10. The other one was around 1700 and negative 34. All right. Let's give that a run. All right, sweet. And let's rerun that. And what do you know? It still works. Our beta values were accepted, and they actually plot a line quite similar to it. So actually, let's go ahead and add in another bit of code here. So what if we wanted to plot these together? So let's say we want a t plot equals np dot, what is it we want to do here? We want to linspace. Let's go to linspace. Linspace, we want to do np of minimum of t and a np dot max of t, and let's put about 100 points on there. Let's see if that gets us anywhere. Shift enter. All right, sweet. So now we are ready to go ahead and plot this. First of all, we need to change this down here. Plot, and we'll change this. Plot. See if that does anything. All right, we're still good. All right, so now we can go down here and actually copy and paste. So let's copy the cell. So let's see, we want to paste, so Control-V, and get rid of that. So now, before we do anything, we want to change some values in here. So we want to change the name of this. We're not dealing with just nonlinear, we're dealing with linear now. So linear, and we want to keep lines. And now we actually want to change the values of the nonlinear A, B, and C. We'll change it to linear values. So linear, linear, and linear. All right, everything should be in order here. So let's shift enter and see what happens. All right, so if we see here, let's actually restart the runtime and take out all these extra lines that are stacked up on top of each other. It's kind of hard to see. All right. All right, see now if we zoom in actually, let's go back. I kind of messed something up here, so let's restart again. And let's see. All right, so if we zoom in here, we see that we have our linear and our nonlinear lines, and they are pretty close. So based on this, we can see that both our linear and non-linear methods of graphing the internal equation in terms of that are pretty similar. Their answers or their results are quite similar. So thank you for watching my video explaining the similarities in linear and nonlinear regression in terms of the internal equation.